Actually, everything is normal now there in France, Lille.
Yeah, now it's better with mask. We can go out.
Satya, you can start.
The places.
Okay. Very good afternoon to all. On behalf of VCAN 2020, we once again welcome you for this presentation, for this session. The title of the talk is Towards Bridging the Terahertz Gap Using Carbon-Based Materials. It's my honor and it's my privilege to introduce the speaker of the session, Dr. Sri Sharan Venkatachalam. He has a PhD in micro and nanotechnologies, acoustics and telecommunications from the Institute of Electronics, Microelectronics and Nanotechnology, IEMN, and a French National Research, CNRS Institute associated with the University of Lille, France. And he has gained a lot of research experience in electronic materials, microfabrication, and device characterization at Europe's leading research laboratories, namely Inter-University Microelectronics Center, which is IMEC Belgium, and also IEMN France. He has got good experience in thermogravimetric analysis coupled with mass spectrometry and spectroscopy techniques such as micro-Raman, infrared, and thin film deposition techniques as well. So currently he is working as a postdoctoral researcher at IEM in France. So with this very short introduction, I invite Dr. Sri Sharan Venkatachalam to give the talk. Thank you.
Thank you, Dr. Satya, for the warm welcome and introducing me to the audience. So now I would like to directly go to the subject of my talk. So this work is actually a part of my PhD with my supervisor, Dr. Jamila earlier. And we worked on carbon-based materials to find an absorber in the terahertz domain. So to begin, I recall the terahertz domain. It is it is the frequency gap that lies between 0.3 to 10 terahertz in the electromagnetic spectrum. That is between the microwave and infrared domain. So nowadays we have diverse applications of terahertz domain. For example, cancer diagnosis. So you can see the two different images, the terahertz image and the visible image, just by the water absorption of the terahertz radiation. It will show the contrast. You can see the red region has more water, so that means it more belongs to cancer. And similarly, in security screening, nowadays the weapons are hidden, and even the weapons are made from ceramics. Ceramic knives are existing, and this can be easily detected using the terahertz radiation, but which is not possible by the other conventional techniques like X-rays. And as a well-known, the telecommunication, the speed of the data transfer rate and the speed of communication can be enhanced using this terahertz radiation. So let us see some of the material interactions with the terahertz radiation. So it consists of three main processes. So if you take any material, the incident terahertz radiation undergoes reflection and partly absorption and transmission. So usually this absorbed radiation is converted as a heat. Okay, and the material properties can be analyzed by the material parameters. For example, the absorption coefficient that says depends on the thickness and the absorption A. And the refractive index for a plane surface, you can calculate the percentage of reflection from the n value using this formula. And why it absorbs, what is the mechanism behind this? So it depends on the material that we use. For example, in gases, liquids, and organics, it is the molecular vibrations that it's like a infrared absorption. And in it's phonons in crystalline and amorphous solids and free carriers in metals, and even the magnetic dipoles can be attributed in magnetic materials. Okay. So what is the problem? Why I discuss this? So absorber can be used for which application? Actually, for many applications, a broadband absorption of terahertz radiation is required. For example, in thermal source, attenuators or radar absorbing materials, even in thermal detectors. But among these applications, we have to uh, determine which material property required for this specific application. In the case of thermal detectors, a low heat capacity and the thermal conductivity and high temperature coefficient of resistance are required, whereas these properties are not really necessary for attenuator or radar absorbing material. So that is the main the motivation for us to find out absorbing material with other properties. It's more multifunctional property. Yeah. And what is the drawbacks of the current absorbers used in commercial thermal detectors? Actually, we find two different kind of materials, that is metal coatings and organic black coating. If you see the metal coatings, we have the absorption. The absorption is given in the red and the reflection is given in the blue and the transmission is in black. As you see, the electrical sheet resistance, as you vary, the properties they change. For example, if you have a thick coating, that is the sheet resistance depends on the thickness of the material. If you have a thick thin film of metal, then they are mostly reflective. And if you have a very thin metal, they are transmitted. And around this magic point here, we have a maximum absorption of 50% only. So we are limited by the maximum absorption in case of metal coatings. On the other hand, if you see in organic black coatings, as a function of the wavelength, they are very dispersive through the spectral. So if you see this, if you take an organic coating and the target of the black coating should be like this, like the red line. It must be a flat, a broad band and absorbing. Whereas we have a dispersive spectrum, it depends on the wavelength that we use. So the penetration depth it changes with the incident radiation. So the longer is the wavelength and you have, it can go deeper. So we have to find out a material that is broadband absorbing. So this is the challenge behind this work. So let us see the terahertz properties of commonly existing materials. So we have characterized the materials according to their electrical conductivity. As you see, the insulators are given here and the conductors are here and the semiconductors are in between them. And the reflection is given in orange and the absorption coefficient is given in the gray. So what you can notice from this diagram is the metals, mostly when they are electrically conductors, they are very much absorbing and also at the same time they are reflective. If you see on the other hand, the insulators like a polyethylene or a diamond, they are transparent and they are partially reflective. The most interesting thing here is if you notice only the carbon-based materials, even based on the allotropy, if it is a sp2 or sp3, the properties are totally different. Okay. So the graphite sp2 bonding has reflective and absorbing, and whereas the diamond, they are transparent and partially reflecting. Similarly, for in the sp3 that exists with organic polymers, they are also transparent. So now we have to find out a balance between the transparent and the absorbing material. So how do we achieve this? So we thought method. So why not we mix sp3 and sp2 compounds to make a disordered carbon, and that can give a variable absorption. But how to mix them? How do we really obtain a homogeneous material? So the approach is we do the pyrolysis of polymers that can result in a disordered structure of carbon, and we don't know whether this disordered structure will be absorbing or reflecting. So that we are going to see in this study. So our approach, in order to understand the mechanism of absorption, we have taken two polymers, organic polymers and a hybrid organic inorganic polymers. And when pyrolyzing them, the organic polymer will lead to disordered carbon, where you have aromatic rings. It's a basic structural units. And in the case of hybrid organic inorganic polymer, we have a composite of silicon oxycarbide matrix, in which the aromatic carbon is embedded. And the objective of this work, as I mentioned before, is to become to get an efficient and broadband terahertz absorber via this route, and also to establish the relationship between the architecture of the precursor and the microstructure of the derived materials. So the outline of my talk is the following. I have three parts. The first part will be about the thermal conversion of polymers. And the second part is the properties of carbon-based material. And the third one is we made a device that is a proof of concept thermal detector that we will see. So the approach, it involves a chemistry route. So first we have the monomers, and these by cross-linking them we get polymers. And these polymers is pyrolyzed to get the residue, and this residue we are interested in as an absorber. So in order to establish the relations between the precursor architecture and the microstructure of the residue, what we did is we did many characterization like thermogravimetry, mass spectrometry, Raman, SEM, and the electrical thermal conductivity and Terahertz properties and so on. So first, the organic polymer that we have chosen is a polyamide. So what you can notice from this structure is the aromatic carbon is already existing here. Yes, you can see with the polyamide group. And the hybrid inorganic organic polymer that we have chosen is a polysiloxane. For example, it's a PDMS gel. You can see it has it comes in the two parts. We have a base polymer, which is a silicon oxygen network with the methyl group on the two sides, and also a crosslinker. This crosslinker contains SiH bond. So when you mix these together, this hydrogen will be removed, and it forms a siloxane bonds to get a soft gel like a polymer. Okay, and we also have other polymers in collaboration with SRI International, a company in USA with Dr. Eagle. So we received samples. With the high carbon content. So they used a different crosslinker like dividend and benzene to make the bonding between the siloxane matrix to get a very carbon-rich compound polymers. So let us see the first thermogravimetry analysis. As you know, it allows monitoring the weight loss of the sample as a function of temperature. So if we see at 1200 degrees Celsius, the residue that is yielding is very much important. This because after heating, how much the higher the residue is, it's better for your device and better for the absorber. So you can see it changes between 50% to 88% based on the precursor that we have chosen. For organic polymer, this is around 55%, and for highest one is 88.2 in the case of polyhydromethylsiloxane with SiH. Okay. Yeah, so here is an example of the thermogravimetry coupled with mass spectrometry analysis of polyamide. As you can see, the main things, the reaction at low temperature, there is an elimination of water. So this can be the desorption of water that was present originally in the polyamide itself. And the main reaction, it occurs between the 600 and 800. There is a homolytic cleavage. It's a well-known degradation of organic polymers. It involves CO1, CO2, and methane. And at high temperature, at around 700 degrees C, there is an elimination of hydrogen, and even above, at a very high temperature, we have the departure of nitrogen. That means the departure of nitrogen, when it leaves, it is a signature of forming an aromatic carbon ring. And this polyamide is well known to make graphitic films. So that is the reason why we have chosen polyamide also. So we also stopped with the reaction at various temperatures. For example, in this figure, we stopped at every temperature, and then we took the Raman spectroscopy of these materials. So as you can see, the polyamide has a characteristic peak of Raman peak of the molecules. With the heating temperature, what we noticed is there is no much change up to 550 degrees Celsius in the characteristics bands, except there is an overall decreasing of the intensity of these peaks. But suddenly at 600 degrees C, we are able to see the peak corresponding to the turbostratic carbon. That is the graphitic band and the D band, the defect band. Okay. By further increasing, we have noticed there is a formation of the organization of these BSUs to have more definite structure of graphite that we can see pronounced also in 2D band. Okay, so that what you have to remember here at this point is the onset temperature for the sp2 formation is 600 degrees Celsius. Okay, that we will see in when we do the Terahertz characterization. So now I do side by side of the other material in order we compare the both materials. So here is the thermogravimetry of coupled with mass spectrometry of PDMS material. This is even more complex. We have the formation of the different molecular levels of siloxane groups that you can notice. But the major reaction, once again, it happens between 400 to 800. Okay. And we will see these steps one by one. So at low temperatures, there is a formation of condensation reaction. That means when you have OH bond and H bond, they make a condensation of water to form SiO Si. And this is happens in salt gel mechanisms. And that we noticed in as a M2Z18 and also M2Z2. And at a little bit higher temperature, around 400 degrees Celsius, we see redistribution mechanisms. So when there is a still presence of SiH, there is a redistribution occurs. This forms also SiH bonds with, so this green part is volatile, okay, that you can detect by mass spectrometry. And in the residue, it forms SiO. Similarly, there is also formation of the cyclic units. It's like this structure which is having a molecular numbers around 207 and 96, and this is well-known mechanisms in case of degradation of siloxanes. And at high temperature, when there is a still presence of SiH, we have the free radical mechanism that is also well known in chemistry. So when you have Si and H, and the radical it moves to it propagates to the chain, and finally it evolves SiC, Si, and then with evolution of methane. So this evolution of methane is a signature for the formation of this SiCH or even SiC bands that you can see the final structure is here. So our technique is very, very powerful. The thermogravimetry coupled with mass spectrometry, we are able to compare using the evolution of methane from various organic polysiloxane precursors, and able to find out at which temperature the formation of carbon starts, even SiC starts. So in order to introduce this, I first introduce the terminology that we use in the case of siloxanes. As you can see, if you have two oxygen, then it's a di-city. And if in the case of the di-molecule, if you have replaced the methyl group with the hydrogen, then we call it DH. Similarly, if you have 3 oxygen, we call tri and DH. And when you have 4 oxidants, it's okay. So this is the terminology. So, and we only followed the M2Z16, that methane, and you are able to see here at with the different precursors and which reaction it occurs. So, for example, the main message that I want to convey from here, I'm not going very deep into this subject. You can always refer the publication of my supervisor, and she is expert of this kind of comparison. And we can see the SiH bonds, they initiate actually the scission. So the SiH, if it's still present, then it makes the the cutting of silicon and metal, and it forms the structure of SiO-Si. So by playing the composition of SiH bonds, we are able to obtain the residues of different carbon content. That is the main message that I want to convey to you. And we noticed the Raman spectroscopy of the different precursors. As you can see, it's the PDMS with the 2 methyl group and PHMS, and here we used TMTVS. It's this molecule as a cross-linker. It has SiH and the high carbon content of the precursor. So what you can notice is we evolved with temperature. They have both, all the materials have the carbon peaks at some point of temperature. So what you can notice is the onset of temperature is earlier. For example, you take 60% HDBB. The onset of sp2 carbon that appeared is around 800 degrees Celsius. And you remember for the organic polymer, it's even more earlier, that is around 600 degrees, which is totally 100% carbon. Okay, so we are able to modulate the temperature to form the carbon that we want to have in our material. So that means the carbon domains, they are under control. This is the message to say. But what happens when we heat at very high temperature, like 1450 degrees Celsius? As you can notice, there is a formation of SiC through carbothermal reduction. This is also a well-known reaction between silica and carbon that forms a SiO, and this is a gas and CO gas. So that we follow the in mass spectroscopy, and we found this. So if you heat at very high temperatures and leave it for a long time, then we reduce the carbon content and we increase the silicon carbide content. And we have to know whether which phase is more important for the terahertz absorption. Okay, so as it is interesting, we also see in the case of the scanning electron microscope, there is a formation of porosity along with the carbothermal reduction reactions. For PDMS, if you leave them at 1500 degrees C for 15 minutes, then there is a porosity. Similarly, for the carbon-rich material 60 dBb, you can see here the formation of holes, and inside there is the different structure that you can notice. So we want to understand what is these holes and how the carbon and the SiC are distributed. So in order to do that, what we have done is we have taken Raman mapping. So as you can see, this phase is SiC phase. What you see right here is SiC, and what you see here is the more organized carbon, because G band is higher than the D, and this we have the D band higher than the G. So this is more disordered carbon. So the Raman mapping, it's actually a powerful technique to see where these carbon phases and how they are distributed in the material itself. So this one was done with collaboration with another lab in France and Orléans with Mohamed Amazi. So to summarize, in the case of organic polymer, the formation of sp2 carbon is at 600, whereas in siloxanes it's around 1000 degrees C. And the yield, they are almost the same that we have chosen. And you see this one is a flat sample, and here you can make it different structures as it is a gel. So coming to the terahertz measurements, so we place the sample and we measure the reflectance and also the transmittance using a vector network analyzers during these bands. And what you can notice is the polyamide that we have taken of different thicknesses, 25, 50, and 125, they are transparent. And this is the commercial absorber. It's a TK-RAM. It's available for terahertz absorber. Once you pyrolyze them at 900 degrees C, then we are able to see the absorption is different for the thickness. So that means it is both the function of thickness and also the temperature of pyrolysis that we will see in the next slide. So here, for the same thickness, that is 125 micrometer, we have measured the transmittance at different temperatures and also the reflectance. We can you can see initially they are transparent and then they are slowly started absorbing. When you go to high temperature, then they become mostly reflective. Okay, so in the next slide, I will show you, I compare this with the metallic limit, that is 50%. I have shown, I explained in at the starting of my presentation, that is with the sheet resistance, how the absorption is changes for the metals. So similarly for the polyimide, you can see that it reached around 800 degrees C. We have the maximum absorption of 50 with the that is the limit of metal absorption. Okay, so for sure, if you take organic polymer to reach the maximum absorption, you must be having heat treating at this temperature. And we measured the electrical and thermal conductivity of these spiralized polyimides. You can see here the ID by IG ratio I have plotted. It's monotonously increasing with the heat treatment temperature. Similarly, the electrical conductivity is also increasing. And you see the thermal conductivity is not, it's a linear almost. So here, the explanation for formation of these structures is explained by Oberle in 1989, where they noticed formation of a graphite sheets of flat layers by polyamide. So initially they are disordered, and then slowly they become stacking of the PSUs along the face to face. That means stacking one over the other. And even at high temperature, then there is a coalescence, that is coalescence between edge to edge. Okay, that forms disordered layers, and finally, if you go even higher, they become flat layers. So this is the explanation of why there is an increase of the electrical conductivity. So now going to the other material, that is the PDMS derived material, where you can see the refractive index, that is given in red, and absorption coefficient, they increase with heat treatment temperature. You remember the onset of the carbon is around 1000 degrees C. So here there is a huge increase of the absorption from this value. And we also measured the time domain spectroscopy analysis in collaboration with the University of Ostrava, Czech Republic. And you can see that the PDMS over this broadband, you remember the graph that I saw for organic polymer, that is very dispersive, but here over the broadband, they are almost flat. So we reached about 80%. And in order to improve furthermore, we thought of making pyramidal samples like this by mold casting technique. So first we make a silicon mold, and then you pour the polymer and detach it, and you paralyze it, you get a pyramidal structure. So this is, here you can see we are able to achieve different sizes of the pyramids by taking different molds, and the size of these molds are suitable to the terahertz radiation itself, the frequency of the terahertz radiation itself. And we also noticed that the net shape is retained. Okay? And we measured the reflectance different angle of 60 degrees, and we can see by increasing the initially flat is reflective, and then by increasing the pyramidal height, they are the reflectance it reduces. So for sure, making the pyramidal structure, there is the changes in the reflectivity. Yeah. So this is the comparison that we made to, you know, some materials, polymers, they are transparent, and the metallics, they are absorbing and reflective, and semiconductors are between them. So we made actually a line that is connecting between these polymers to metals by making a bridge of these with these materials. So that's why the absorber that is not existing in this domain, we are able to make with the modulation of the carbon with this chemical approach. Okay. And finally, I do not have more time, so I present the thermal detectors. It is actually you have the absorption of radiation, and that becomes heat, and you sense the temperature and as a voltage or current. There are many detectors that is existing, that is well known. So I am not going to deeper into this. So I would like to show you, we placed, you know, this is a temperature platinum thermometer. On the top of this, we kept our pyramidal absorber, you can see. And this consists of this PDMS derived material. And we measured the responsivity, that is the voltage that is developed in the platinum thermometer over the power of incident radiation. You can see it well behaves. We have obtained the responsivity of around 0.1 with the extrapolated curves that is given by the theory. Okay. And the speed of the detection that we can detect by the time constant. So if there is no absorber, it's very, very fast. That means the platinum itself, it absorbs. So this is the blue curve corresponds to no absorber. And with absorber, we enhance the responsivity. At the same time, we also increase the thermal time constant. Okay. So when we compare with the other detectors, we take the noise equivalent power. So this says about the sensitivity of the device. So our work is well positioned in the other existing devices. So in conclusion, I would like to tell that the chemistry approach, it gives a lot of possibilities to modulate the carbon content in this nanocomposite material that is suitable for efficient absorption of terahertz. And the microbolometer that we have developed is the proof of concept is a very good comparison with the existing ones. And it seems another advantage of the PDMS is they are resistant to oxidation. And sometimes we can also use this material as a thermal source. So I thank you very much for your attention. And this work is not done alone. It's they have a lot of collaborators and help from the technicians who are in the laboratory of IEMN and other places. So I thank you very much.
Thank you, Shri, for the interesting and very informative talk. Due to the time constraint, I'll ask a couple of questions. One question from the participant. Can you explain the reflectivity in texturing surface?
Yeah. So with the texturing surface, actually we have the pyramidal structures. So when there is a flat surface, then you have the specular reflection. It occurs at 45-degree angle. So as you have the pyramidal structures with different heights, then there is a formation of second chance for the wave to get trapped in the material. Okay, as they have more surfaces, so we increase the surface area of the material to enhance the reflectivity. So to decrease the reflectivity and enhance the absorption of the radiation.
Okay.
Hope it's clear to you.
And what are the advantages of pyrolysis method over the conventional nano?
Yeah, in the case of nanocomposite, if you want to mix the carbon with silica matrix, then the mechanical mixing, you cannot reach good control over the carbon. With the pyrolysis method, we have the molecular architecture that we control in the polymer side, and as you heat them, there is a distribution of carbon uniformly in the material.
Okay, okay. And can you comment on the thermal stability of the PDMS derived materials?
Yeah, the main advantage of this polymer derived ceramics is they are very, very stable at high temperature because the carbon, they burn around 600 degrees C as they are enclosed in the silica matrix, CO2 matrix, so and even SiC matrix. So they will be stable even if you heat around 1400 or 1300 degrees Celsius. So this can be used for harsh atmosphere and also oxidizing atmosphere, as it is glass that cannot be oxidized more.
Okay. Okay. So we once again thank you for this wonderful talk. Thank you for accepting our invitation in short notice, and thank you for the talk once again. On behalf
Thank
of
you,
the team,
Dr.
we
Satya.
thank you.
It's my pleasure to have
Thank you, Dr. Sricharan. It was indeed a nice lecture. Yeah, thank you once again for accepting our invitation. We'll be in touch.
Thank you.
Thank you. Have a great day. Take care.
Yeah. So, Heidi.
Thank you. Thank you, Shri.
Yeah, bye-bye.